Okay, so let's continue to look at the other three distributions. First one is called the Poisson distribution. This is a very, very useful distribution. When we're going to use this, it's, when we counting, something in an interval of time. For example, if we are counting, the number of the customers between 1 to 2 p.m. In McDonald's, so at that time, we will often use this Poisson distribution and as an approximation for this real life scenario here. And so typically, you see, so for number 4, so normally we will, so when we count, the occurrence of certain events in a time interval, okay, in time interval. So we're going to use this Poisson distribution. Another example, see, if we want to count in, again, the number of customers who visited McDonald's from 1 p.m. to 2 p.m. Okay. So suppose from the previous data, we know that on average, there are, 50 customers visit that store. Okay. But we do know that each day is different, right? Maybe there is a day only 10 customers to visit to the store between 1 and 2, or sometimes maybe 70. Okay. So we're going to use this random variable to show the number of customers as a Poisson random variable, with the given parameter on average, 50. Okay, so so often we will write it down as x is a Poisson random variable with lambda. This lambda, you can think about it, back to the example we just discussed. It's like the average, number of customers visiting McDonald's during that time interval based on the previous data here. Okay, so often we will write it follows a Poisson distribution with lambda. So the PMF here actually, and by the way, the range, as you can see, is going to be 0, 1, 2, 3, right? Because it's possible that although it's very, very rare, but it is possible that there is no customer, right? But it's very, very rare. So the probability, the mass function, which is defined into this way, okay. So it's e to the power of negative lambda, lambda to the power of k over k factorial, okay. So when k belongs to R, of x, 0 other y. Okay, so that's so. Oh, and by the way, as you can see that the Poisson distribution is also a discrete. X is also a Poisson random variable is discrete random variable. Okay. Okay, so moving on, let's look at another two here. The first one is called a uniform distribution. What this uniform distribution does, as you can see, for example, if you want to select a number uniformly at random, let's say from the interval from 1 to 2. Okay, so this is where the uniform distribution starts with. Okay, so what we said here is, as you can see, for the uniform distribution here, this random variable is going to be a continuous random variable. Okay, and so if it's a continuous one, so we're going to looking for it's the probability dense function. Okay, density function here, and so we're looking for PDF, not PMF anymore. Okay, so this is what we can describe. A continuous random variable x is to have a uniform distribution on the interval from A to B, given an interval. This is the notation. And then the PDF which is derived as the reciprocal of the length of that interval, which is b minus a. Okay, if when x is greater than a, less than b, and 0 if x is greater or equal than b, or x is less or equal than a. Okay, so that's the uniform distribution. It's a continuous one. The application normally is like we said, we select number uniformly at random from a given interval. Okay. Last one, the exponential distribution. So what about this one, the exponential distribution? Well, this distribution is also very, very useful. What it does is it models the time elapsed between events. Okay, between events. Okay, and so this one, we also have a parameter given here, which is also called a lambda here. So, and of course, because it's time elapsed between the events, so as you can see, so you can think about it, it's the number, the time between the number of the customers who arrived at McDonald's. So for example, if the first customer arrives at 1, second one arrives at 1:05, third one arrives at 1:08, fourth one arrives at 1:09. So you can see that those times elapse here, and then between these customers, we can use this exponential distribution to model that part. And typically we will write it down as right into this way, because it will have its one of the parameter lambda, and keep in mind that this lambda must be greater than 0. Okay, so this is what we write it down, and then the corresponding PDF is going to be lambda e to the power of lambda x, where x is greater than 0. Okay, and 0 other y's. Okay, so that is some background about the exponential distribution here, and I think in the following videos, or later on, we might talk more about the application of this exponential distribution. Okay, so I'll stop here, and thank you for watching.